Hello, and we're back for Chapter 16, Part 2. So we're going to pick up where we left off. Now we're talking about stream order. And this is a system that was created by Arthur Strahler to look at various streams and tributaries and to kind of compare like to like. He created this system that ranks the order of a stream based on how many tributaries it has. So the higher the order, the more tributaries it has. So for instance, a first order stream is very small and has no tributaries. So this would be like the small creek you might find in the forest reserve. When two first order streams meet and join, then that becomes a second order stream. So a second order stream has two tributaries. So you can kind of say it's a bigger stream. And then for a stream order to go from second to third, it must meet another second order stream. In other words, each time a stream order increases in number, that means two streams of equal order met. So let me show you what that looks like. Right? This is where the river begins, way up here in the mountains, all these little tributaries. These are all first order streams. But when two of them meet, they form a second order stream. So number one here meets this number one. Now it becomes a second order stream. Now, when the second order stream here meets this one, then it becomes a third. And when this third order stream meets this third, it becomes a fourth. But what's important to note, here's a first order stream joining the fourth. The first order stream has no tributaries. It's a small river by itself. It doesn't increase the fourth order stream. The only way the fourth would become a fifth is if it met another fourth order or similar magnitude stream. So to give you a sense of how this works, most of the streams in the world are third order or less. So the Chicago River, I believe, would probably be actually a second order stream, if that, right? But there are exceptions. The Mississippi River is a 10th order stream. The Mississippi River has tributaries like the Ohio and the Missouri and the Arkansas and the Red that are pretty big rivers in their own right, okay? The Amazon River actually is a 12th order stream that is the highest in the world. One of the tributaries of the Amazon, the Rio Negro, is bigger than the Mississippi River. Another aspect is permanence. We always assume that streams are always there. The Chicago River doesn't really go away, but that isn't always the case. If you have a dry climate, you might have an intermittent stream. It might dry up. Or if it's a very small, maybe a first order stream, it might dry up in the summer. That happens actually in the desert as well. You also might have an ephemeral stream. And here, an intermittent stream is dry only part of the year. An ephemeral stream is dry almost all year, and it actually only flows briefly, usually in a desert after a heavy storm. So you'll see a lot of dry riverbeds in desert areas. The permanent stream is just that, the Chicago River. It flows year-round. It doesn't dry up. Okay? And the last one is an exotic stream. This is a stream that would probably be an ephemeral stream, but it's permanent because it has so much water in it from somewhere else. So the Nile River, when it gets to Egypt is such a hot, dry desert. If it wasn't for the fact the Nile River starts 2,000 miles to the south in the rainforest of Africa and has enough water to be permanent, it would dry up. Another thing that can happen, especially, we talked about this before, the water table. If it's a dry season and there's less rain, right, the water table will drop. And if the water table drops below the bottom of the river, all the water in it will soak into the ground, and you get a dry stream channel. Interestingly enough, people have actually done this as well. There are streams that are usually permanent, but we've changed them. So a good example is the Colorado River, the same river that makes the Grand Canyon. It starts in Colorado, flows through Colorado and Utah and Arizona, Nevada, Mexico, and Nevada, California. When it gets to Mexico, it is now dry. This is the actual former stream. You can see where it used to come in right here. It actually is dry. We take so much water out of it. The Colorado River is a main source of water for Los Angeles and for Phoenix and for Las Vegas, as well as Mexico, so that we've basically taken all the water. And it actually looks like this most of the year. And that's been disastrous for the wildlife. one thing they've been doing in the last couple of years is they lessen how much water they take out in the spring. So they let water flow down. So you can see here is March 20th, 7 days later. They let this pulse of water flow down, almost like a spring flood. And it helps the plants and animals kind of hang on for a little bit longer. But that is a big issue right there. All right. Now that we talked about streams a little bit, the next part is erosion. So I mentioned before that weathering is taking big rocks and making them into small rocks. But erosion is what most people think about. Erosion is the movement of these materials, and streams do a large part of that. Water is one of the most powerful agents. It moves a lot of stuff. That's why we use it to wash off sidewalks in our cars, right? So water flows to the oceans. Water always follows gravity. So anywhere on Earth above the ocean, right, water is going to seek its own level. It's going to try to flow downhill. So this gravity causes streams to form channels. Those channels basically cut little gouges into the earth, and it pushes rocks and dirt, and it moves chemical weathering agents and all these minerals, and it transports all this material, either broken or dissolved material from weathering, in what we call fluvial erosion. So here's how it starts. Imagine this right here is a big piece of flat land. There's no river, very, very high up in the mountains, and the rain falls, right? And it forms these tiny little channels called rills. I mean, the width of your pinky maybe, right? But the rills all flow downhill, and where they meet, they form a gully, which is just a smaller rill, and they get deeper. And as they get deeper, more water flows into them, and gullies connect with more and more rills and become deeper and deeper. And they're basically cutting down and forming the beginning of a river. This is what a river looks like when it forms, right here. Here's the person standing here, right here. These areas in between, where there's no water, they call that an interfluve, which just means between the water. Now, this process, by the way, will always cut this way, downhill. But it looks like this goes back this way, these rills, almost like they're going up the hill. Okay? Over time, they'll get a little bit longer this way as more and more water fills them. That's called headward erosion. I wouldn't worry too much about that. Now, stream discharge is how we measure all of this movement. When we look at rivers, we say how much discharge do they have? In other words, how much water do they move? We're measuring the volume of water. So if we were to stand at the Michigan Avenue Bridge and we measured how much water was flowing past, that would be the discharge of the Chicago River at Michigan Avenue. So we have a thing that's called a hydrograph that measures it. And there are various things that affect it. So stream discharge is never static. In other words, it fluctuates by climate, by season, if the surface is really absorbent or not. If there's more water after a rainstorm, more water flows into the river, discharge will increase. If it's dry, it hasn't rained in 2 months, or we pave all the ground next to it, those will also affect discharge. So it's basically a mathematical principle. If you make discharge what you're looking for, Q, right? Then Q is the area times velocity. So you remember back, right? If you want to find the area of something, you do width times length. Well, if we want to find the velocity of a river, we basically measure how much area right here. We measure at a certain point. So this is Michigan Avenue, right here in the Chicago River. We measure how wide it is, 300 feet. We measure how deep it is, 25. So 300 by 25, and that is an area right here. So 300 times 25, let's just say it's, my math is horrible, 1,000 square feet. Then we times it by velocity. How fast is it moving? So it's moving 1,000 square feet every minute. And that is basically what you're doing. You're measuring how much water is moving. They sometimes have a little thing in the river. It looks like a little wind vane. And the faster the water turns, the faster this turns. And we measure the speed. Okay. This right here is an example. You kind of see it's covered up right here. This is attached to a stream. We have these stream gauge monitors along rivers that we track. And what happens is this little float here floats in a pool of water that is connected to the river. If the discharge of the river increases after a rainstorm, this increases. and then the float here rises, so we can measure that. And so what happens is this lets us know if this river got deeper but the same width, the stream area went up, right? Because we've increased the A. So mathematically it goes up. And what this shows you right here, that is streams increase their height. We call that stage. How high is it, the stage? The discharge goes up. Now, one thing that we notice, especially in an urban environment, is that we see a dramatic change in stream discharge. Urban streams have a much different way of discharge after a heavy rain event. What happens is this. Urban environments, like the city, have many impermeable surfaces. These are surfaces that water can't soak through, like a street, or a parking lot, or a house. And what happens is, if you have a lot of impermeable surface, when the rain falls, you think about out before people built houses, right? When the rain would fall, some would soak into the ground, and some would flow into the river. But if everything can't soak into the ground, so downtown Chicago, when it rains, right, there's really no open ground. It's all sidewalk or building. Where does all the water go? Right into the gutter, which flows into the river. All of a sudden, you're dumping more water into a stream faster after a storm. And so what happens is, in urban areas versus rural areas, you can have the same size stream and the same amount of rain, but in an urban environment, the discharge of a stream will go up really, really fast, much higher, much more than a rural stream. It looks kind of like this. These two lines, the green line and the blue line, measure the discharge, how many cubic feet per second this river is moving. And they're similar sized streams. And then on January 1st, we had a storm, and both areas got the same amount of rain. But you can notice right here, the green stream is in the city. And look at the discharge. It goes up easily 3 times higher than the rural stream. And it goes up faster. Conversely, it also drops faster. So how does that play out? Why is that an issue? Well, this right here is the north branch of the Chicago River. This is Foster Avenue. Here's Kimball. This is Northeastern Illinois University, Northside College Prep. So this would be North Park University. And this is the north branch of the river in a very urban setting. These are all neighborhoods. Now, most of the time, it looks like this. It's a very small, shallow stream. This is probably 6 inches deep at its most. You could walk right across it. But in the last 10 years, every spring, we have these small floods when the snow melts or a storm comes through. And large areas of that neighborhood are flooded. People's basements flood to the point where now the streets are 3 to 4 feet deep. And what's happening is, as Chicago has grown and become more urban, and let me go back to that map, all this area that used to be open field is now permeable or paved. The water goes in there quicker. If you were to zoom out and follow the North Branch, it goes up into Lake County. So we're talking Libertyville, Highland Park, Gurnee, that whole area. And in the last 30 or 40 years, much of that area has become suburbs, just like here. So all of that area that used to be open, wet marshland is now paved. So a lot more water is coming into the Chicago River. So much so that we now notice flooding every 2-3 years. And it's very expensive. So the city has decided and just finished actually building a special tunnel. They built this big, big tunnel about 50 feet underground. It actually goes right under Foster Drive, Foster Road. And what happens is when the river begins to flood right here, and this is Pulaski Avenue, if it goes too high, it enters the tunnel. And this tunnel takes all this water and dumps it in the North Shore Channel here, which is much deeper and can handle that. And it bypasses this whole area that used to flood. Well, why is that a concern? It cost $70 million to do that. So we are paying that cost, $70 million of having impermeable surfaces. I mean, that's a lot of money. That's money that could be used for many things. All right, I'm going to pause that right here. We'll come back with Streamload in chapter 16, part 3. So sit back, go have a cup of tea. We'll see you in a bit.